Module 13, Statistical Significance and P-values. Section 2, P-value fallacies and data torture. What are some P-value fallacies? Because I told you in the last section that the P-value is one of the most misinterpreted statistical element in the history of sciences, and people are actually torturing the P-values also to prove the what is in their mind to be proven. The same thing, the fallacy that I told you, the cognitive bias called confirmation bias in the first module, if you remember it. So some of the most common P-value fallacies or misinterpretation of the P-value is including: the P-value is a probability of rejecting the null hypothesis. This is untrue. That is not the case. The P-value definition has nothing to do with rejecting the null hypothesis. So a high P-value proves that the null hypothesis is true. Again, that is wrong. It has nothing to do with null hypothesis being true. 1 minus P is the probability that the results will hold up when the experiment is repeated. Again, that is a fallacy. That is totally wrong. 1 minus P is the probability that the alternative hypothesis is true. Again, wrong. The P-value is the probability that the null hypothesis is true. Wrong. P-value is the probability that the result was due to the sampling error. Again, wrong. All these are fallacies. So there is a related term called P-hacking or tweaking or data torture. So this is not simple simply because of the misunderstanding of the P-value, but this is more like a deliberate attempt to get low P-value to prove your hypothesis, alternative hypothesis, and declare your findings as statistically significant by getting very low P-value. How do you do that? So before that, there is an interesting anecdote explained by Vickers in his 2006 papers. So statistician is asking to a surgeon, "Oh, you have already calculated the P-value?" Then the surgeon said, "Yes. And I did something called multinomial logistic regression." Then the statistician said, "Really? How did you come up with that?" Then the surgeon said, "Well, I tried each analysis on the SPSS drop down menu, and that was the one which gave the lowest P-value. So it made my results significant." See, this is a big problem, So you are doing the same test with multiple. So to do different tests is not at all difficult. SPSS, by the way, is a statistic package, especially targeted to the social science researchers, and it is quite robust. But I won't recommend that to the biology students because SPSS is not really meant for biological data, and we have much better softwares. I suggest you to go with GraphPad Prism, which is really good software, and Sigma Plot is also quite good for the sciences, but GraphPad Prism is especially good for not mathematical biology students, that the very intuitive way to come up with the diagrams. So to perform the statistical test in these packages is very easy. Just drop down and click, then you will get a P-value. But how did you choose a test? The rationale of choosing the test is more important. And that is what I'm trying to teach you through this entire MOOC course on biostat and mathematical biology. So if you make lots of comparison, that is what you call the problem with the multiple comparison. If you do a lot of tests, again the P-value what you got is artificial, and it's very well prone to type 1 error, that is false positive error. The chances to make the false positive is extremely high if you do a multiple comparison. What some other ways that the scientists come up with this P-hacking is through different tests, parametric and non-parametric, and picking one with the lowest P-value. So these are all constitutes to the multiple comparison. So you have to correct that P-value there are formal methods to correct that P-value. So P-hacking, tweaking, data torture, all these are synonymous terms to indicate this deliberate attempt to reduce the P-value. Some of these non-methods, well, all these are cheating, okay? So some methods include dynamic sample size and something called ad hoc sequential sample size, and stop when the P-value is lower than threshold. Slice and dice your data set to get the lowest P. Cherry picking the data set to get the lowest P. That means that you are not using the entire data set, only you are using the cherry picked data set. I've explained about this cherry picking in my first module. Then play with the outliers. Remove one or more selectively to get the desired P. Again, outliers have already been explained to you, and manual outlier removal is wrong. It's totally wrong. You have to use a test like Grubb's test, to remove the outliers. So route method, you can use it. I've explained to you in one of the earlier modules. All of these above, all these P hacking things are cheating and constitutes to serious scientific misconduct. So beware of it. Another related term is called stargazing or stargazing. So what is that? It's overemphasizing the P values because of the star, especially if you are putting that in a graphical display. So the bars above which it's just say 1 star, 2 star, 3 star, and just by looking at the star and making conclusions about it, that is a wrong practice. Decision based on the P values all depends on the threshold significance level. So which is chosen as an arbitrary. I've told you this many times. So this is the main reason why the borderline P values makes not really any sense at all. So P values depend on the sample size. It is easy to get a very low P value with huge sample size with tiny effect, or tiny sample with huge effect. So you will never know which is the reason why you got a very low P values. And P value answers the question, is there a significant evidence of the difference? Not the question, is there an evidence of significant difference? So when you look at the P value, probably naturally the question that comes to you is that, oh, P value answers the second question here. That is there an evidence of significant difference? That is not the case. It is only that there is a significant evidence of the difference. So difference might be very tiny, or it could be just negligible. Yet the decision based on the P values, statistically significant. So that could be that. There is a related term called HARK. What is that? Hypothesizing after the results are known. So once you come up with your results and then you modify your earlier hypothesis, that is plainly wrong practice. Many people does it. That is a very bad one. So when a researcher first look into the data and using the data to pose a hypothesis. So HARK is cheating and constitutes to serious scientific misconduct. Another form of HARK is changing the objectives of your PhD thesis or an MSc dissertation. After the results are known, you should not do this. That is also a form of HARK. Another related term is called Hingeside bias. So as I explained to you in the first module, which is a cognitive bias in which people subconsciously change their earlier belief or memory and results, after the results are known, also called I know it all along effect. So it happens to us, right? After the results are known, for example, if you watch a cricket match and India wins the match, then you can always say, oh well, I already know that India is going to win that match. They played very well, and India lost the match also, you will say the same way. Oh, I know it all the way. That is what I was expecting all way through. So it all depends on the result. That you are tweaking your memory. You are changing your memory to conform to the result. So that is called the Hingeside bias. So some of the common mistakes are belief that the statistical hypothesis testing is essential part of all statistical analysis. That is a mistaken premise. It is not that essential for entire statistics. The statistics doesn't always depend on statistical hypothesis testing. Belief that if the result is statistically significant, the effect must be large. I told you the effect could be very tiny, insignificant, trivial if you have a huge sample size. Again, that will lead to a very low p-value. Belief that the statistical hypothesis testing is for making conclusion, again wrong. That is not for making conclusions. In reality, hypothesis testing is for crisp and therefore handy decision making. You can just say yes or no, so there is no ambiguity in your decision making. So that is what the statistical hypothesis testing is for. So in summary, there are a large number of misconceptions about the p-values as the concept is hard to understand. So this include p-value is a probability of rejecting the null hypothesis. In fact, it is not that case. So, the terms p-hacking or p-tweaking or data torture all convey the same meaning. So, it's actually done, deliberately done to decrease your p-value, to declare that the differences are significant, which is a wrong practice, and this also constitutes to scientific misconduct. Overemphasizing the p-value is sometimes called stargazing, looking only at the star, the asterisks of the graphical displays. Hypothesis testing based on the p-value entirely depend on the threshold p-value, that is alpha or significance level, which is totally an arbitrary in nature. It is easy to get a very low p-values with huge sample size with tiny effect, or tiny sample with huge effect. So don't always say that our samples were tiny and the sample real effect is very high. That might not be the case. P-value answers to the question, is there a significant evidence of difference? Not, is there an evidence of significant difference? So these two terms are totally different. When a researcher first look into the data and use the data to pose a hypothesis or changing the initial objectives are known as hypothesizing after the results are known, or HARK. Again, that is a misconduct. Another related term is known as Hingeside bias, a cognitive bias in which people subconsciously change their earlier belief or memory after the results are known. These are also known as I know it all along effect. Thank you so much for watching this video, and I will see you soon.